All right, let's dive deep into capacitance. We're going to go way beyond the basics here and really explore how to derive the properties of capacitors right from first principles. By the end of this, you're going to have a powerful toolkit for analyzing pretty much any system, no matter how wild its geometry gets.
Okay, let's just start with this incredible image. What you're looking at is a Lichtenberg figure, which is basically fossilized lightning trapped inside a block of acrylic. This is the raw, chaotic power of separating charge and then letting it all go at once. Our goal today is to understand the device that was literally designed to tame this energy, the capacitor. So, what exactly is a capacitor? At its heart, it's just a device for storing electrical energy. And you know what? It's surprisingly simple. All you need are two conductors, we'll call them plates, and you just separate them with an insulator. That insulating material is called a dielectric, and it's actually super important to how the capacitor works, as we're going to see. The single most important property of a capacitor is its capacitance, which we represent with a C. It's really just the ratio of the charge Q stored on the plates to the voltage V across them. The unit for this is the farad, named after the one and only Michael Faraday. And trust me, as we're about to find out, 1 farad is a huge amount of capacitance. So here's our game plan. First, we're going to build a really powerful, universal method for calculating capacitance from scratch. Then we'll put that method to the test on 3 classic shapes: the parallel plate, the spherical, and the cylindrical capacitor. And finally, we'll wrap up by seeing how these ideas actually show up in the real world.
Okay, so how do we actually figure out the capacitance for any random system of conductors? Well, it's not guesswork. There's a systematic 4-step process that comes directly from first principles. This is going to be our core toolkit for everything we do today. Here it is, our 4-step plan. First, we just imagine putting a charge plus Q and minus Q on the conductors. Simple enough. Second, we whip out Gauss's law, one of Maxwell's equations, to figure out the electric field between them. Third, we calculate the potential difference, the voltage, by integrating that electric field along a path from one conductor to the other. And since the E field is conservative, it doesn't matter which path we take. And finally, the easy part. We just plug everything into our definition, C equals Q over V. And here's the magic. The charge Q we started with, it's going to cancel out every single time, leaving us with a result that depends only on the geometry of the system. It's beautiful.
All right, let's put this method to work with the classic example, the one everyone starts with, the parallel plate capacitor. It's the configuration most people think of, and it's the perfect first test for our new procedure. This setup couldn't be simpler. We've got 2 identical conducting plates. Each one has an area A, and they're separated by a tiny distance d. We'll assume one holds a charge of plus Q, and the other holds minus Q. Step 2, let's find that electric field. Now, for big plates that are close together, the field between them is basically uniform, pointing straight from the positive plate to the negative one. Its strength is just the surface charge density, sigma, divided by epsilon naught. And remember, epsilon naught is just that fundamental constant that tells us how electric fields propagate in a vacuum. Since sigma is just charge per area, Q over A, the electric field is simply Q divided by A times epsilon naught. On to step 3, the potential difference. Because our electric field is nice and uniform, that line integral becomes dead simple. The voltage V is just the electric field strength E multiplied by the distance d. So we just substitute it in our expression for E, and we get V equals Q times D all over A times epsilon naught. And now for the grand finale. We take our expression for V, plug it into the definition, C equals Q over V, and look at that. The Q's cancel out, just like we said they would. We're left with this wonderfully elegant result. C equals epsilon naught times A over D. This is huge. It tells us the capacitance only depends on the geometry, the area of the plates, and how far apart they are. That's it. So just to put the size of a farad into perspective, right? Let's say you wanted to build a 1 farad parallel plate capacitor, and you make the gap between the plates just 1 millimeter. Well, each plate would have to be 10 kilometers on a side. Yeah, 10 kilometers. That's why you don't just find 1 farad capacitors lying around the lab. Okay, let's move on to our next case and see how our method holds up with a totally different geometry. We're going to apply the exact same 4-step process, but this time to a system with spherical symmetry. The process is identical, but the calculus will look a little bit different. So here's our new system, 2 perfectly concentric conducting spherical shells. The inner shell has a radius r1, and the outer one has a radius r2. And, you guessed it, we'll put a charge of plus Q on the inner shell and minus Q on the outer one. For step 2, we use a spherical Gaussian surface, and Gauss's law gives us a field that points straight out, radially. It has the exact same magnitude as a point charge at the center. E equals Q divided by 4 pi epsilon naught r squared. Then for step 3, we just have to integrate this non-uniform field from the inner shell to the outer shell to get our potential difference, V. After we do the integration and then apply C equals Q over V, we end up with this really nice result. And look, once again, the capacitance only depends on the geometry of the system, in this case, just the inner and outer radii of the shells. This is a theme you're going to see over and over in electrostatics. It's this deep, fundamental connection between the geometry of a system and the laws of physics. For our last derivation, we're going to tackle a system with cylindrical symmetry. And this geometry is incredibly important for engineering, especially when you need to guide and shield electrical signals. So what we've got here are two long, concentric conducting cylinders. The inner one has a radius r1, the outer has a radius r2, and they both have a length L. We'll assume a charge of plus Q on the inside cylinder and minus Q on the outside one. Okay, you know the drill by now. Same procedure. We use a cylindrical Gaussian surface, and we find the electric field falls off as 1 over r this time. Then we integrate that field to find the potential difference, and because we're integrating 1 over r, we end up with a natural logarithm. Finally, we divide Q by V to get the capacitance. And there it is. It depends on the length of the cylinders and the natural logarithm of the ratio of their radii. And this result is absolutely fundamental to designing things like coaxial cables. You know, the cables for your TV or internet. In those cables, the capacitance per unit length, C over L, is a super critical parameter. It's what determines the cable's impedance and how well it can carry a signal without distortion. This is a direct, real-world application of the math we just did. So now that we've mastered the theory for these perfect idealized systems, let's take a look at where capacitors actually show up in the real world, from the circuits inside your phone all the way down to the very cells in your body. Now, capacitors obviously come in all shapes and sizes, but this one on the right is especially cool. It's a variable capacitor. See, when you turn that knob, you're physically changing the overlapping area of the plates. And what does that do? It changes the capacitance, which lets you do things like tune an old radio to a specific frequency. It's a beautiful, direct, mechanical application of that formula we derived, C equals epsilon naught A over D. And check this out. This is a mind-blowing example of capacitance. The membrane of every living cell in your body is a capacitor. It separates conductive fluids inside and outside the cell, and it maintains a voltage of about 70 millivolts. But it does this across a distance of just a few nanometers. If you do the math, that creates an electric field of about 10 million volts per meter. That is an enormous field, strong enough to cause a spark in the air. It's just a stunning example of physics at work in the biological world. You know, all of our calculations today, they all made one key assumption. We assumed there was nothing but a vacuum between the conductors. And that brings us to a really important question, one that's going to lead us right into our next topic. What happens? What happens to the electric field, the potential, and ultimately the capacitance when we fill that space with an actual insulating material, a dielectric?